Hey everyone, thank you for watching this video. If you are working with GIS, Geographic Information System, remote sensing, or just you're curious about geospatial modeling, this is like something that you will want to understand. So let's get started. Okay, today I will talk about INLA for geospatial modeling. Before that, I would like to explain some like basic concept about like correlation, spatial autocorrelation. So what is correlation? So correlation is a statistical relationship between two variables. So we can improve this explanation in this graph. You can see like the temperature, when the temperature is going up, immediately the humidity is decreasing. This is like the behavior that we call like correlation, you know? Correlation, it's like kind of the dependence between two variables, right? In that context, spatial autocorrelation gonna be focused just in one variable. In that case, just for instance, that this digital elevation model, this is black point, they have similar values, right? So if I make like the comparison with those, that means that it's like that is like a weak correlation, between this group and this one. So that is what I call autocorrelation. We can find like a strong autocorrelation. Maybe we can get like a weak between both. The first one, the second one. That is highly related. That we call like the first law of the geography, where everything is related to everything else. But I think that are closer together are more related than things that are further apart. So in this case, INLA appear as a potential approach to fix the challenge. So INLA, what is INLA? INLA is like an integrated nested Laplace approximation. It's a computational approach that allow me to fit complex model. When I say complex model, that means like latent Gaussian model. That is like at the core of INLA. INLA tries to fix this kind of the latent Gaussian variable models. But at the same time, INLA it's pretty famous for spatial temporal model because it's possible to work with big, large data set like in remote sensing. And in combining in mix with SPDE, the stochastic partial differential equation, provide like much better result to explain the spatial variation, right? So let me explain something about the core of latent Gaussian models. As I mentioned before, INLA is working with latent Gaussian model. But what is latent Gaussian model? So we can assume that we have like our data set like temperature, soil moisture, or vegetation, right? In that case, I have like a specific data set for temperature. This temperature is following like exponential distribution, but in your case, that can follow different distribution, right? We know that this behavior of this temperature could be explained by my covariate and plus something else that I have not measured yet, right? So we know right now like covariate could be like wind, elevation, all those variables can provide some aspect to explain this behavior of my temperature, right? So what I call like something else, it's the same like unobserved variable. It's something that I have not measured that I can see, but I strongly believe that it's affecting my distribution. That's what I call latent Gaussian variable. But in that case, this approach make like a strong assumption, right? This assumption is like this unobserved variable follow a Gaussian distribution. So, but we know like this Gaussian distribution is affected by a specific hyperparameter, but this hyperparameter follow a different distribution, not necessarily like Gaussian distribution. Remember, please, like the strong assumption here is the latent Gaussian um, field. As a linear predictor, this is like a way to compile everything. We can observe here we have our coefficient for covariate, like the intercept and random effect model. INLA has the opportunity or can support a different model like independent and identically distributed Gaussian random effect or like a random walk or autoregressive model to explain the variation, right? So latent Gaussian like INLA has the ability to compute the posterior distribution of latent Gaussian variable and hyperparameter. So, sorry. Here, as I mentioned before, INLA, we can use INLA with this specific package in R. We can set here like my first covariate, my second one, and I'm going to set my model for random effect. In that case, it's like the same independent and identically distributed Gaussian random effect. So this particular model could be sometime uh, that can be like a strong assumption, right? Because in my area number one, that means like in my area number one doesn't affect the random effect in my area number two. But we know that in reality it's so hard to get this kind of the situation because everything is connected, right? So another like more complex or robust model could be like random walk or autoregressive mode. Random walk, basically I'm going to estimate my current value, but it's highly related with the previous one. That means that I'm going to use the previous one value to estimate the current value. Instead of the autoregressive model, it's the same, but here I'm going to add like a specific coefficient or parameter. Mean that I'm going to, for example, estimate that point, but using like the previous one. I can use like the two previous values to estimate like my current value. Um, that can provide better result compared to the independent and identically distributed Gaussian random effect. Maybe sometimes it's associated with like some realistic behavior, with instead of our data. Still, as a comparison, to provide like an example of both approaches, we have here our regressive model and random walk. This is like a data set of missing vegetation in a specific area here in Idaho, but we try to fit our data using our regressive model and random walk model. That data it's like for 2004 to 2020 probably, and instead of the missing vegetation value proportion, we can observe like some strong changes using our regressive model compared to the random walk. That's like the effect of this correlation coefficient here and like a random walk. Maybe we can observe some changes in that land cover in this missing vegetation that could be as a result of like some restoration process project. It's a good discussion. So okay, at the moment I have been talking about like temporal autocorrelation, but what happened with spatial autocorrelation? How can I explain like this variation? So in that case, we are going to use SPDE, like stochastic partial differential equation. But I don't want to talk about like the mathematical background behind that. Just I'm going to provide like the key aspect of in SPDE. SPDE is like a powerful tool in like INLA work that it's has the responsibility for identifying like spatial dependency across all my area, right? So we know right now, like try to model all my data point could be computationally expensive and sometimes possible, right? So a stochastic partial differential equation allows me to approximate those spatial dependency by breaking my area into smaller. This smaller area is what I call like basic function here, right? First, what I need to do here is like establish my mesh. Then using like my covariance, my Matérn covariance to set like the smoothness and all my surface, right? So this Matérn covariance function, it's gonna be able to set how far those points are related each other, right? It's gonna be able to set like the correlation in a specific area. You can see um, each triangle, this mesh basically is a is a net of triangle, and each triangle has associated like basic function. And at the end, this basic function with like the Matérn covariant Matérn function, gonna be able to set the smoothness or correlation in all my surface, right? Um, and as application all of INLA and SPDE, I would like to present like an example of this approach. Right now, this is a paper to study the spatial temporal changes in terms of the soil organic matter in China using three different data sets. Right now, they they implemented like environmental covariate elevation, annual precipitation, water vapor pressure, and they run this model. They we can see like the coefficient, covariate coefficient, our latent process, and yeah. So that was like the models they were able to run to implement this model. We can see like this latent process is like a combination between temporal and spatial approach. So they are using like autoregressive model that I talked before. And this, instead of the spatial autocorrelation, they were able to use like um, kind of like matter covariant function similar that is called like linear fractional SPDE, because sometimes this matter covariant function could be computationally expensive to set all these like changes. We can observe like the result using that approach. Like this is the content of some with specific variants. We can observe like a higher variant here compared to another one. We can check like there is like a big difference between like this time collection data. Sorry, here 20 and 2000 and 2006. They are like closer compared to this the first like data set. We can like one of like a really important conclusion is like INLA has the opportunity to explain much better like this variation compared to other methods. So in a nutshell, INLA the application basically we need to set like the triangle mesh. Like we need to construct like our SPDE and stack our data and run INLA. According to the previous paper, they mentioned like the really important or crucial aspect about this match. Maybe it's highly related to the accuracy in our models. We need to be careful in that step to get good result. So, and thank you so much. Thank you for watching this video. Thank you for being at the end of this presentation. This was like the initial part of INLA in the work. And please feel free to drop a comment. I will be happy to see your comment. And yeah, I will be posting more videos about like remote sensing and statistical approaches. And that's all. Thank you guys. See you next time.